Hello everyone, and welcome back to this series on optimization methods. Today we're going to change our fields just a little bit and focus on an optimizational problem that is very famous in the realm of economics and trading theory, and it's called the Kelly Bet Criterion. Now before we actually get into what is a Kelly Bet, we need to first review just a couple elements from economics, in particular microeconomics. So a utility function, which I'm going to be denoting by little letter u, represents an individual's preference over various outcomes x in its domain. So as a very basic example, let's suppose that x is the amount of money that you make or that you win from a bet. So, and let's define our utility function u of x to be equal to the square root of x, right? Obviously here, since we're assuming that x cannot be negative, that means we're assuming that we cannot lose any money in this particular object. So I guess you could view this as profit. So if this is u of x, then its derivative with respect to x, u prime of x, as we already know, is just going to be 1 over 2 times the square root of x. So let's briefly interpret what we mean by a utility function by graphing both of these objects here, right? So if we graph u of x is equal to the square root of x, then we already know that the graph of that is going to look like that. So the more money that we make, the more happy or satisfied we become. But if you notice here for this particular utility function, if we graph its derivative, which is going to be this function, that's u prime, notice that our utility function's derivative, which we sometimes refer to as the marginal utility, is decreasing, right? Therefore, if we want to increase a certain amount of utils, I guess you could say, or satisfaction, we need a lot more accumulation of wealth. Some people also refer to this as the law of diminishing marginal utility, right? Which usually is associated to risk aversion, right? Because obviously if you're winning more money, you probably are betting a lot more upfront, which means that you're risking a lot higher of a percentage of your portfolio, which means if you lose it all, then that pretty much ends your betting sequence. Okay, so let's actually list down a couple very important observations about this particular structure. And notice that sometimes we refer to this as a concave down utility curve if its derivative is negative, or its second derivative is negative, right? Because it looks like a frown instead of like a smiley face, like a cup, as people say. So, as our x increases, our utility increases, which means that we prefer larger values of x over smaller values of x. And of course, this function is chosen. You could change it to be a completely different utility function if you want. And also, as x increases, u prime decreases for this particular one. So this is usually called, again, diminishing marginal utility, right? Which means the more you get, the less satisfaction comes from it. Yes, you do get some satisfaction, but the amount of satisfaction that you get from each util as you get higher and higher and higher decreases. And that's why you sort of see this decreasing marginal utility curve, right? So that's the basics of utility functions that you need to understand for the Kelly Bet criterion. Now, our second definition that we need to understand in terms of utilities is the following, because x is usually going to be a random variable. So let's suppose that f of x, or p of x, represents the probability mass or density function for x. Keep in mind, if x is discrete, that would be a probability mass function. If x is continuous, that would be a probability density function. Then the expected utility is given by the following formulas. So how do you find expected utility? So if you're familiar with expected value, then these formulas should be familiar to you. So the expected utility is going to be equal to, for discrete, so this one's going to be for discrete, is going to be equal to the sum across all possible values, x, of our utility function times its associated probability value for that particular value of x. Or in the continuous case, the expectation of u will be equal to the integral across all values of x, so let's say generally minus infinity to infinity, which could be 0 in some of those regions, of u of x times its associated probability density function with respect to x. So that's how you calculate the expected utility, given a particular utility function u, and assuming you already know the probability distribution of that random variable x. Now, before we actually get into the Kelly Bet criteria, let's do a quick calculation example of how to calculate the expected utility for a, for example, continuous random variable. So let's assume we're working with the same exact square root utility curve, which has the law of diminishing returns for utils. And also let's assume that the random variable x is continuous with a probability density function associated to an exponential distribution with rate parameter lambda. And in case you don't remember anything about the exponential function, the exponential PDF actually looks like this particular object, right? Here, that height value is going to be equal to lambda. And that rate parameter obviously controls how fast it decays. And one other important property, the expectation of that random variable is going to be equal to 1 over that lambda variable. Okay, now with this probability density function and this utility function u, let's calculate the expected utility, the general form, and then I'll use a numerical example for lambda once we are done. So the expected utility, since we're in the continuous realm, will be equal to the integral across the domain, which is going to be 0 to infinity in this case, of our utility function, square root of x, times our probability density function, lambda e to the minus lambda x dx. Okay, so once we have this, I'm going to just use a u substitution on this lambda x term, so I just have e to the minus something. So if I let v be equal to lambda x, then dv be equal to lambda dx, forcing dx to be equal to dv over lambda. Once we have that, keep in mind, when x is equal to 0, we're going to have v is equal to 0. And when x is equal to positive infinity, we have v is equal to lambda infinity. And since lambda is positive, that's also going to be infinity as well. So our bounds for our integral stay the same. Also, if v is equal to lambda x, that means x is equal to v over lambda for the substitution on that x term there. So once we have that, then we can just bring in our substitution values. So the expected value of u, or the expected utility, will be equal to the integral from 0 to infinity of the square root of v over lambda times e to the minus v times dx, which is dv over lambda. Notice that these lambdas do cancel, which is actually very, very nice. And then we can also factor out this 1 over square root of lambda there. So we're going to have the integral from 0 to infinity of v to the power 1/2 times e to the minus v dv. And this integral is a lot more nicer. And you should recognize the structure. If you've taken differential equations, you should recognize this as a Laplace transform evaluated at omega is equal to 1. If you are also familiar with some of your special functions, you should recognize this as a gamma function. In particular, this is 1 over the square root of lambda times the integral from 0 to infinity of v to the 3/2 minus 1 e to the minus v dv, and I've represented 1/2 as 3/2 minus 1 because that is the structure of a gamma function evaluated at 3/2. So that means this is just precisely 1 over the square root of lambda times capital gamma of 3/2. And if you know some of the special values of gamma, then you should know the half values in particular. So gamma of 3/2 will be equal to the square root of pi over 2. So the expected utility with this particular utility function and probability density function for x is just going to be equal to the square root of pi all over 2 square root of lambda, which, keep in mind, is just a number. So with this particular information, let's just do a quick numerical example. Let's assume that the expected value for x is going to be equal to 30. So let's assume x is your return on investment or something like that. So we expect $30 on average. That means that the lambda value is going to be equal to its reciprocal, which is going to be 1 over 30. So with this particular utility function, the square root of x, what is the expected satisfaction for this particular value, which obviously should be dependent on the expected value of the random variable that we have. And from our calculations, we see that that's just going to be equal to the square root of pi all over 2 times the square root of lambda, which is 1 over 30, which is approximately equal to 4.85, right? And the interpretations of utils is totally subjective, depending on the context. So we expect to have 4.85 utils of satisfaction given these particular utility and probability density functions. Now that we know the basics of utility and expected utility, now let us figure out what is a Kelly bet. So now let's get into the fun stuff. Suppose that capital Pi represents your total portfolio value, and let's assume you are trying to decide what percentage are, between 0 and 1, of your total portfolio value that you want to bet, so that your long-term net return is positive. So let's assume that you can either win or lose a bet. So we're going to have two cases here. So let's look at case 1. So case 1 is that we lose the bet. So what would your new portfolio value be? So it's going to be your old portfolio value minus the percentage R of that portfolio value that you put up, right? So this was your bet. So this is your total normal portfolio. And keep in mind, notice that we can factor out pi here. So we're going to have pi times 1 minus R. This shortcut is going to be very useful in practice. Now let's look at case 2. So case 2, this is where we win the bet. What is going to be our value, our new value of our portfolio in this scenario? So our new total portfolio value will be equal to our old plus that value. So this is going to be equal to R times and then B pi. Right? Now I'm going to tell you what B is in just a moment. Before we do that, that's going to factor into pi times 1 plus RB. So what is this B? Well, B is going to be associated to your prize, right? So this is going to be associated to our prize. So our prize is that you receive your bet plus B times your bet, right? For example, you get 50% more than your original bet or something like that. So typically B would be a decimal that is bigger than 1. We'll look at a couple examples in case it's not clear to you, right? So B is just going to be representing your prize factor, or sometimes people call it your bets win ratio. So what does the Kelly criterion do for this world, right? So the Kelly criterion optimizes the expected logarithmic utility. So what is logarithmic utility? Well, logarithmic utility will be a utility function like that, right? So that's going to be your x, and that's going to be your u of x. Now, this utility function is slightly different than the square root of x utility function that I mentioned earlier. Now, it's still concave, Because keep in mind, if that's your utility function u, then the derivative of natural log of x is 1 over x, so we still have that law of diminishing return structure. But the only difference between the square root of x curve and the natural log of x curve for 0 is we had 0 utils for making no money. Now we have negative infinity utils when we make no money. So it actually has a negative impact on our utility, right? But the Kelly criterion optimizes the expected logarithmic utility. So what is the utility function here? So the utility function with respect to pi is going to be equal to the natural log of our portfolio, right? And keep in mind the variable is r here. We want to know what percentage of our portfolio should we invest in order to optimize this particular function, right? So let's actually list out what our expected utility is. So our expected utility, keep in mind, we either have a win or a lose in terms of this bet. So we're going to be doing sort of like a discrete expected value. So it's going to be equal to the probability of winning, which I'm going to note as p, times the value, which is going to be the natural log of pi times 1 plus rb. And then we have the probability of losing, which I'm going to note by q, and that's going to be the natural log of pi times 1 minus r. And the goal here is to optimize this particular function with respect to r and find the value of r that satisfies that particular relation. So this is the expected value of the logarithmic utility. Right? Now, if we didn't use natural logs, keep in mind that's how much money we would get, and that's how much money we would get if we lost. Right? Now we're taking the logs of those particular numbers. So let's take the derivative. So what is the derivative of the expected value of the logarithmic utility with respect to the percentage of our portfolio that we invest? So that's going to be equal to what? So we have some chain rules going on here. P is a constant. So we're going to have P divided by pi times 1 plus rb. The variable here is b, so pi is just a number, so the derivative of pi will be equal to 0, and the derivative of pi rb will just be equal to pi b. And then we're going to have what? So we're going to have q over pi times 1 minus r, and then chain rule again, the derivative of pi will be equal to 0, and the derivative of minus pi r will just be equal to minus pi. Now keep in mind we seek to optimize this function, so we want to take this object, set it equal to 0, and solve for r. Solve for r. Right? And we're going to call that value r star. And I leave it for you to verify that this will be a maximum for this particular function. But that's just another quick calculation using a second derivative. Or, you could look to the left and look to the right and see if it's positive then negative, like a sign test for the maximum or minimum. Now, once we set this equal to 0, what will we get? So let's actually clean this up just a tad bit, just in case you're not comfortable with the math. So we're going to have pi p b all over pi 1 plus rb. And then we're going to have minus pi q all over pi 1 minus r. That's going to be equal to 0. Notice that we have some pi's canceling there and some pi's canceling there, so everything is actually very, very nice. And then we're going to have some cross multiplication, so we're going to have p b times 1 minus r minus q times 1 plus rb is equal to 0. Keep in mind our goal is to find r, or r star, in this particular equation. So let's distribute that out since r is on the inside. So we're going to have pb minus pbr minus qrb equals 0. Now, isolate your r terms, move everything else to the other side. So we're going to have what? So minus p, let's actually factor out that r. So let's bring that r out. So we're going to have r times minus pb minus qb is equal to pb plus q. Then we're going to divide both sides by that interior term. And then that's going to give us what? And let's, of course, make sure we haven't made any silly errors here. Let us see. That PB should be negative because it was on the left positive, and that is positive on the right. Okay, we're good. So once we have that, we're going to have R is equal to, notice we have a negative sign there, negative sign there, and let's actually revert that around. So we're going to have PB minus Q all over PB plus QB. And that's in some sense the equation for R, but we can actually clean this up just a little bit if you're very insightful, because this is, keep in mind, PB minus Q over, and if we factor out a B out of the bottom, notice we're just going to have P plus Q. Remember that P plus Q are complements of each other, so P plus Q is actually just going to be equal to 1 regardless of what P and Q are. So this actually simplifies very, very nicely. And we have that R star is equal to PB minus Q all over B, right? And this is referred to as the Kelly bet, right? So this is the percentage that we are aiming for, that we will decide to invest of our portfolio in order to maximize the long-term growth, assuming a logarithmic utility function with respect to our total portfolio value, right? So that's the Kelly bet. And of course, some people will actually rewrite this as R star, because notice we can actually divide those fractions out, and we can write this as P minus Q over B. That's another way of writing the same exact representation. Now that we have derived the Kelly bet, which is this magical proportion of our total portfolio value, now let us get into an actual working example to sort of see how it works. Let's consider the following game. Suppose you're playing a game of cards and everybody draws one card. You will win if you draw a jack, king, queen, or ace, and you will lose otherwise. Keep in mind, since everyone's drawing one card at the same exact time, each of these events are actually independent of one another, so it actually doesn't even matter if you're playing this game by yourself or not. So the prize for this game, if you win, is you will win your entire original bet plus 85% of whatever you wagered for the first. So if you were to play this game over and over again, and you want to make profit, how much should you wager, assuming that you have a logarithmic utility curve? So this is, of course, a Kelly bet setup. So what is the solution? So the solution is actually very straightforward. So first off, find the probability of success, i.e. winning. So there's a jack, king, queen, and ace, 2 of each on red and 2 of each on black. So that's going to be a total of 4 times 4 out of a total of 52 cards, which is going to be a probability of 16 over 52, or reduced as 4 over 13. So if 4 over 13 is your probability of winning, that means the probability of failure is just this complement, which is going to be 9 divided by 13. So now we need to figure out what our value of B is, and that's associated to our profit. So the value of B is going to be equal to 85% of the original, and you're not supposed to count your original in this calculation of B. So that's just going to be 85, right? So that's your profit. Once you have your P, your Q, and your B, now we can calculate our Kelly bet. So the Kelly bet, which I'm going to denote by R star, again is going to be equal to PB minus Q all over R. So that's going to be equal to what? So P is going to be equal to 4 over 13, B is going to be equal to 0.85, Q is going to be equal to 9 out of 13, and again, R is going to be equal to, it's not going to be R, that's supposed to be B. We don't know what R is. And B is going to be equal to 0.85. Once you actually do out those calculations, you're going to get hopefully a number between 0 and 1, but in this case, you're actually going to get negative 0.5068. So you're like, oh, I need to take 50% of the money they're going to give me before they even give it. That's actually kind of awkward. So if you get a Kelly bet that's negative, what does that even mean? Well, it means don't bet, because it's less than 0, right? So don't bet. So when a Kelly bet turns out negative, that means usually the odds are not in your favor at all for winning over the long term, right? So this is just a big, big gamble. And to some people, maybe that's okay. So don't bet, bad game. So a natural question that might come from this is, what should the profit payout actually be? Profit payout be for us to want to play using a Kelly Bet criteria strategy. So that means we want this to be greater than 0, which means that PB minus Q must also be greater than 0 as well, because B should be, if it's negative, then it's really bad. B should be positive, so the numerator should be positive as well. So that means PB minus Q must be greater than 0. So our focus is B. That's associated to the profit. So generally speaking, that means B must be greater than Q over P, which is the odds in favor of losing. And in some sense, that makes sense. So B must be greater than Q over P, which means that B must be greater than, for our example, 9 over 13 all over 4 over 13, which is going to be equal to 9 over 4, which has a decimal is 2.25. Okay, so 2.25. So in some sense, they need to give you 325% of your original bet or more in order for you to have a positive net return in the long term if you have a logarithmic utility. Now, with this information in mind, let us slightly manipulate the example that we originally had. So example modified. So now let's assume that you see another game, same rules, just different prize. So you're going to win your bet back and then plus 324% of your bet, right? So that means in some sense B is going to be equal to what? So this is going to be equal to B, which means you take your original bet, that's going to give you 424% of your bet. That's going to be your total net return. So if this is our new prize, that means what? So if you end up betting 52%, so let's assume this $52 is your Kelly Bet value. If you bet 52, and let's assume also that we win, you will get $52 plus 3.24 of that 52, which means you're going to get 220 plus 48, which is approximately $170 on top of the 52 that you already had, right? So that's actually a lot of money, right? So is this a game that is worth playing? So let's actually work out the math. So solution. So our Kelly bet under this particular structure is going to be, again, PB minus Q all over B. So that's going to be equal to, if we rearrange that, that's just P minus Q over B. Now, if you want to make this problem even more fun, if you actually have an additional loss, not just you lose your 52, but you lose some more money, you can actually divide this by another scalar, A, to sort of have a more generalized Kelly Bet criteria strategy, right? But here, A is going to be equal to 1 for this example. So for our numbers, what are we going to get? So that's going to be equal to P, which is going to be 4 over 13, and then minus 9 over 13 divided by our value of B, which is 3.24, which is approximately 0.0940. So that is our Kelly Bet ratio. So let's actually work out an example to sort of see how much money we're going to get if we play this game. So let's assume, or let's suppose, our total portfolio, pi, is equal to $500. And we want to play this game. So game 1. So how much money should we play this game? So by our Kelly bet, we're going to bet this $500 times our R star value that we just calculated, so that 9.4% of that. And this is going to be equal to 47.01. So that's how much money we will put up. Because keep in mind, if you put all of it up, you can't play again, even if you lose, right? So if we lose this, we're still going to have like $450 some left, and we can still play a few times, right? Now, some people will actually go even less than that. Some people will actually do a half Kelly bet or a quarter Kelly bet. So keep in mind, usually people use an or less structure here. So if we lose, and that's a sad story, that means our new total portfolio is going to be equal to, keep in mind, pi times 1 minus R star, which is going to be equal to $452.94. And again, let's assume that we want to play again, right? So game 2, we're going to wager, or we're going to bet, the same exact structure. So we're going to do pi nu times this r star, and that's going to be approximately equal to $42.59 or less. Right? Keep in mind, all of the theory is here, so as long as you have a logarithmic utility and the trials are truly independent of each other, then in the long term you should still be having a net gain. But keep in mind, if you lose twice in a row, in some sense you are just definitely unlucky. Keep in mind, only wager what you're willing to lose. So if we win, so everyone's happy here, what are we going to have? So that means pi nu will be equal to, so general structure is going to be equal to pi times 1 plus r star b, and that's going to come out to approximately $652.31. That's actually nice because we got like $150 in profit, so that's wonderful. Now, just because you made $150 doesn't mean you should increase your betting by $150. We still should be using a Kelly Bet strategy because it's possible that we lose all of that and then we can't play it anymore. Right? So using a Kelly Bet structure, we will bet, again, pi nu times r star. And for this particular structure, when we multiply 652 by our r star, that's going to give us approximately, of course, a little bit more, so it's going to be 61.33, and again, or less. Keep in mind, some people will do a half Kelly Bet or a quarter Kelly Bet, depending on how much they're willing to lose. Overall, that is the main strategy associated to the Kelly Bet criteria and also how to use them in practice. Hope you enjoyed this video, and I'll see you in the next one. Take care.